Okay, now we're talking about waves. First of all, waves come in two different varieties. There's transverse waves. That's our most common type that we deal with all the time. And then there's also longitudinal waves. Now, longitudinal waves are also called compressional waves, and that actual name actually makes more sense, as we'll see in just a minute. Now, there's quite a bit of vocabulary for this section, and some of it may be new, some of it not so new. Transverse waves look like that. Few housekeeping things. That's called a crest. That's called a trough. Crest is top, trough is the bottom. Amplitude. Amplitude is the height of the wave, but the important thing to understand, it's the height from the rest position. It's how much it's disturbed from the rest position. So it's the middle to the top or the middle to the bottom. So they will talk about a peak-to-peak value, which would be that point to that point. Amplitude would be 1/2 of that value. The other thing that's important here is wavelength. It may sound like a Captain Obvious thing. Wavelength is really nothing more than the length of a single wave. Now, as far as words for wavelength, we're going to use lambda, the Greek letter lambda, which looks like an upside-down Y. For amplitude, we'll use capital A to represent amplitude. Key thing to understand here is waves transmit energy. In this case, the energy goes that way while the particles go that way. So for example, if you're stuck out in the ocean and you're bouncing up and down, you're going to bob up and down on a boat like this. You're going to be moving up and down while the energy goes sideways with you. Now, let's take a look at a longitudinal wave. Longitudinal waves are harder to draw. Easier to show. I can show it with, Slinky in class, but harder to draw. Now, you have an area where the waves are close together, then they spread apart, then they get close together again, then they spread apart, then they get close together again. That part is called a compression. That's why the term compressional wave actually makes more sense, because you have an area that is compressed. This is a science word. The spread out part is called a rarefaction. That's not a word you're going to see probably any place outside of a science class. It's the spread out part of a wave. The wavelength is from the compression to compression, or rarefaction to rarefaction, either way. The compression corresponds to the crest in the transverse wave, and the rarefaction would correspond to the trough in the wave. And waves are all around us. Common types of transverse waves: light and everything that behaves like light, X-rays, microwaves, gamma waves, all of those, radio waves. The most common type of compressional wave is sound. And you see this from seeing the woofer of a speaker. If you have a speaker that's shaped like this, and we've all seen woofers like this, you know that the speaker goes back and forth like this. Compress the air, pull the air back. Compress the air, pull the air back. Same thing your vocal cords are doing down inside of you. So it creates a wave that does this. Close and then spreads farther apart, and then close again like that. I can't draw. So let's make sure. Now, a couple equations that come into play in this. First of all, two words that we use a lot in here: frequency and period, which we talked about briefly already. Frequency is the number of waves per second. Period is the number of seconds for one wave. It's pretty easy to see that those are reciprocals of each other. We use F for frequency, capital T for period. Frequency is equal to 1 over T, 1 over period. You also see it written with just a normal script F. We use capital F for force, so it won't be capital F. Other equations that are kind of valuable for this is speed. Now, remember, speed is equal to distance divided by time. If I go back to like week 1, speed is equal to distance divided by time. Well, speed of a wave, and this is the speed of a crest. So make sure we understand that it's actually the speed of an individual crest on that wave. So V is equal to distance over time. Well, it turns out V is also equal to frequency times wavelength. which is kind of neat. Now let's take a look at the units. We know speed should be in meters per second. Let's make sure it actually works out that way. Well, frequency is in waves per second. By the way, that's also called a hertz. If we multiply that times the meters per wave, which is what wavelength is, although we traditionally just write meters, waves cancel out, leaving you with meters per second. The math and physics gods are happy. Now, key thing to understand about waves. V depends upon the medium. So in other words, how fast a wave travels depends upon what it's traveling in. So air at 20 degrees Celsius, the speed of sound, let's talk sound because that's a familiar thing that we hear all the time, is approximately 343 meters per second, 3.5 football fields in a second. It does vary with temperature a little bit. That's why that 20 degrees is important. But if I go underwater, it's now moving at about 800 meters per second. I mean, think about dolphins and whales communicating. They can do it over really, really long distances because the wave travels faster and actually better. If I go to something like steel, we're somewhere in the neighborhood of 1,500 meters per second. So the speed does depend upon the medium that it's in. And by the way, sound in a vacuum is equal to 0. There's no sound in a vacuum. No, in space, no one can hear you scream. Have fun.